Hello and welcome to another electronics video. So here we're going to talk about how to get the best scale for any graph in an easy way. So to do that, we are in a digital era, right? So I'm going to use a computer to demonstrate that, but that doesn't mean that the method I'm going to show is only applicable on computers or on digital graphs or anything of the sort. No, you can apply it to physical graphs also. I'm just trying to simplify the process by doing it on computer. Now remember that we created a graph on Microsoft Excel in the previous video. In case you haven't watched it, kindly go and check it out. We customized this graph on Microsoft Excel, as you can see, and this can be taken to be a page of the graph. So anyway, I'll be moving between Microsoft Excel and Microsoft OneNote because I will have to be quite creative when trying to solve this graph question on computer. So to do that, I'm going to first take this page to Microsoft OneNote, so kindly give me a minute. So here we are. Wondering how I did it? Well, actually I went to Microsoft OneNote and clicked on Insert. There's this option for screen clipping, so when I clicked on it, it showed me an arrow and I highlighted the part I wanted to appear on my Microsoft OneNote. So here we are. I'm going to be using this space for my little calculation or small writings. So anyway, before that I actually drew lines to represent the x and y axis, and while making that I had to consider that an ideal graph is supposed to cover about 3/4 of the whole graph page. So your graph is not supposed to be at this corner here or somewhere here. It's not supposed to be just occupying an obscure corner of your graph. It's supposed to spread evenly. So now that we have our graph paper and we have our axis, how do we actually select the best scale for a graph? Now to do that, you have to consider your values. Now this is a set of values for a stress strain graph. I considered the fact that my values for stress are actually okay. They are not that confusing. They can be easily plotted on a graph because I can easily maybe get a scale of a multiple of 20 or 50 to represent all this. But then the problem lies in the values for the strain. Most people get confused with values which have many decimal places, something like this. So what I normally do is I convert my values if they're somehow skewed. I try to convert them to easier manipulated values. Now to do that, I just simply take the lowest value and convert it to standard form. For example, this I converted it into 4.72 times 10 raised to power minus 4. So I subsequently converted all the values into multiples of 10 raised to power minus 4, and I inserted the 10 raised to power minus 4 up here. Now I have a set of values which don't look too confusing, and I can use them to plot my graph and it won't be much of a problem, just the way I have nicely looking values here. Now when I come back to my graph, I can decide which scale to use. Now usually scales taken in multiples of 2 or 5. They're easier to use. Sometimes we take multiples of 4, but multiples of 4 are actually doubles of multiples of 2, so it's almost the same thing. For example, if you take each box to be 4, you are just indirectly saying each small box is 2. So now, considering these values, which scale am I supposed to use here? To do that, you take a look at your lowest and your highest value. Now remember that when drawing your axis, you have to consider something first. You have to make sure that you don't have negative values. That's when your graph is going to look L-shaped like this. If you had positive and negative values, then it simply means that you have to make provisions for negative values. For example, it will have to look something like a cross somewhere here, so that you'll have space for negative x-axis and negative y-axis. But then in this graph we don't have negative values, so our graph can start from the origin around here. Now back to our matter, that is when we are discussing about which scale to use. The easiest way to know which scale to use is to consider your lowest and your highest value. Now here we can see that if we are plotting this against this, we are going to use these values, not this. When we are plotting this against this, our graph is going to start from the origin, so that's okay. Now our highest value for stress, that is the y-axis, is actually 234. It's not the last value here, because stress strain graphs usually go up and then come down as they approach breaking points. As for the strain values, the extension increases with increasing load, so our largest value is 1100.79 multiplied by 10⁻⁴. Remember that. So that means if we are going to create a scale, it has to accommodate 1100 and about 1, and on the x-axis, and 230, about 235 on the y-axis. Now most standard graphs that I usually see around have 10 boxes on the horizontal side and 12 on the vertical side. But then how many do I have here? Already I made a provision for space here and here, so that I can write my values, my units, the names of my axis and things like that, because normally a graph sheet doesn't have much space by the side or at the bottom for you to make your graph to occupy everything. So it's better if you leave some space where you can write your stuff. So now by studying these values, I have already mentioned that my largest value for y is going to be about 235, and my largest value for x is about 1101. So I'll count my boxes, my available boxes. On the y-axis I have 1 2 3 4 5 6 7 8 9 10. So I have 10 boxes. Now what is the best possible value that I should assign to each box for me to be able to accommodate 235 on this axis? If I try 20 multiplied by 10 boxes will give me 200 as the highest value, so it's not going to be okay. Then I will just try 50. I can try 50, 100, 250. But then if I use 50, my graph is going to be too close. That is, it's not going to be spread out. So in that case I'll use 40. When I use 40, it's going to be 40, 80, 120, 160, 180 and 240. So if you notice that you still feel that your graph is a bit close together, you can shift your graph a bit upwards such that it will start from this point instead of this point, so that it will look more balanced on the page. As for the y-axis, that is here I'm going to have 40, 80, 120, 160, 200 up till 240. Now remember that this is our axis for stress. I'm going to try to write stress, and it has a unit of Newton per millimeter square. As for the x-axis, according to my values, I have 1100 and approximately 1 to be my largest value, and I can count my boxes. I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 boxes. So if I divide 1100 by 8, it's going to give me about 140, but that's not a realistic scale to use. The reason being, we have small boxes in here, right? And each box, if you take a scale of perhaps 140, each box here is going to be 140 divided by 10, that's 14, and it will be a bit complicated when you are plotting your values, when you have maybe something like 500.79. How are you going to get 500.79 when you have a scale of 14 to each small box? So it's going to be a bit complicated, and that's the main reason why we mostly use multiples of 2 or 5 for our graphs. For example, you can see this is 40. That means each small box is going to be 4, and if each small box is going to be 4, each tiny box is going to be 4 units. That's 4 Newton per millimeter square. And a small box here, that's at this point we have 20 units. At this point we have 40. When we are looking for 60, we simply say 60 minus 40 is going to give us 20. So after giving us 20, we can divide 20 by the value of each tiny box, that is 4. So we'll know that after 40, when we are looking for 60, we simply have to count 20 divided by 4, that is 5. We have to count 5 tiny boxes to get 60. So that's the principle behind it. Now for this x-axis, it's not practical to use 140 or 150 because it's going to complicate our life when trying to plot values like 339.3 and things like that. So it will actually be easier to, since 100 won't accommodate all, that is because since we have just 8 points, we can't say 100, 200. It will just stop at 800, and our largest value is 1100. So the best thing to do is that we use 200. By using 200, at least it gives us a small box at this point to be 100. So by having 200 here, if we have 200 here, we'll have 400 here, we have 600, 800, 1100 and 1200. So the value of each small box is going to be 20 divided, each tiny box, sorry, it's going to be 200 divided by 10, that's 20. So each of these tiny boxes has a value of 20. So when you are looking for 500, 500 is in between 400 and 600, right? So the value of each tiny box is 20, right? So you take the distance between 500 and 400, that is 500 minus 400 is 100. So you say 100 divided by 20, that will give you 5 tiny boxes. So you count 5 tiny boxes and you'll know that your 500 is somewhere here. So what if you are looking for, say, 720? Now 720 minus 600 is giving us 120, right? So 120 divided by 20 is 6. So it simply means that your 720 is 6 tiny boxes away from 600. That is, your 720 is somewhere here. So understood. Remember that this is string and it has no units. Now if you have to plot this graph, already it is going to start from the origin somewhere here, and then your second value is 22.6 against about 22.6 against 4.72. so your 22.6 is, this is your 20. To get your 22 is it's not up to one, it's not up to what I'm trying to say is that after getting your 20 to be here, 2.2 is not up to 4, so your value of the addition to 20 is not up to a tiny box. So ideally your point is going to be somewhere in between your line for 20 and another tiny box, because after one tiny box after 20 is supposed to be 24 and your value is not up to 24. So you try to, it would have been easier if this is a physical paper, you know how to plot your value at least in between these tiny boxes. Here it's not going to be much possible because my pen is a bit thick. So anyway, that is the philosophy behind scaling and plotting of graphs. So already you know on Excel we had actually already plotted the same graph on Microsoft Excel earlier. You can check out our previous videos, and it gave us something like this, right? So they use 50 as their scale for the y-axis, but as you can see their graph is not very high, and usually our physical graphs are taller than this, so it's actually better to use a more encompassing graph. But from the x-axis they use 0.02, which is actually the same as the value we use, because remember that all these values are raised to the power of times 10 raised to the power of minus 4, right? So if you're going to multiply each of these values by 10 raised by minus 4, for 200 it's going to be 1 2 3 4, it's going to be 0.02. so voila, we actually use the same scale with a computer. So when you know the techniques behind this, it won't be difficult for you to plot graphs, and you won't be hooked up wondering which graph to use. You won't be cleaning and recleaning and wasting time when you have to complete an exam. And remember that in material science, graphs such as this, you actually have to get the graph correctly for you to solve other questions, such as determining mechanical properties such as Young modulus and stuff like that. So anyway, we are going to treat how to get those mechanical properties in another video. So see you soon. Thank you for watching, and do well to check other videos, like, subscribe, and share with others too. Leave your insights, your suggestions, your comments. They're all welcome. Goodbye.